All right, so here we go with our third day of limits. So you've seen these types of discontinuities, like you've seen these different types of things happen in pictures. Now it's time for you to know the name of them. So this first one here is called a removable discontinuity. So that's when you basically have a hole, right? So a hole in the graph, and that hole might have a value elsewhere, or it might not. So like if this point was not here, that would be fine. That would still be it's called removable, because what would happen if the hole was like filled in? So I could remove the hole by naming a point right here. Okay, so by saying, oh, there's a point on the graph at 2, 1. So it just so happens that this point does not fill the hole, but even if it was filled, it would have still been a hole to begin with. So, you know, this x value 2, the function might be redefined somewhere else, or this might be missing. Okay, and it's called removable because you could fill the hole. You could remove the hole by filling it in. All right, and the next one is called a jump discontinuity, and so that's pretty simple to see. A jump is like when there's a gap in the graph. Now that's not to say it's an asymptote. So it has to be like where the left side comes to one place and the right side comes to another. So basically there's a gap, and your left and right limits will not agree. Okay, now these could both be open. This could be, you know, closed, open. They can't both be closed, because if they were both closed, it would not be a function. But if there's a gap, so imagine you're walking along this curve and you're like, oh no, I have to jump over here. All right, so a jump discontinuity is when there's a gap. Okay, and a hole, it's like you're walking along and you step in a hole, right? Okay, and the last one, the type of discontinuity, is called an infinite discontinuity. And that should be very simple, because your graph goes off to infinity, or it goes off to negative infinity. So right here, there must be an asymptote. So these occur when you have a vertical asymptote. When there's a vertical asymptote, what happens is your graph goes off to infinity, and so that's called an infinite discontinuity. Okay, so what we're going to do here is we're going to name the type of discontinuity, if there is one, and I'm just going to say where it is. Okay, so this right here, state if the function is continuous or discontinuous, and skip parts B and C if it's continuous. Okay, then we're going to tell what type it is, removable, jump, or infinite, and we're going to say the x value where it occurs. And every once in a while there might be a couple discontinuities on there. Okay, so this right here, this gap, so that's a jump discontinuity. So this function is discontinuous. Okay, it's discontinuous, and there is a jump discontinuity, and I see that happening at x equals 3. Okay, all right, right here, I see people going off to infinity. All right, positive and negative. There is an asymptote, a vertical asymptote. So this is discontinuous. The type of discontinuity would be a infinite, and this happens at x equals 1. Oops, focus here. All right, so on the next one, that is a hole. So that is called a removable discontinuity. This is discontinuous. It is removable. It was not removed because the red spot's down here, not up there, but it happens at x equals 3. The next picture, same as the last, but there is no fill-in spot. There is no number place defined for x equals 1. So actually x equals 1 is undefined, whereas over here x equals 1 is equal to 0. So this is discontinuous, still removable at x equals 1. All right, down here. Well, this function something funny is going on. You know, you have one line, then another line, so there's like some strangeness here, but I don't see any holes, I don't see any jumps or gaps, I don't see any asymptotes, so this is continuous. Nothing, it's weird, but it just goes along. You can keep driving along. So we don't need these. For the next one, I see a vertical asymptote, things going to infinity, so this is discontinuous. It happens at x equals -3, and it's infinite. All right, next one. I definitely have a gap here, so that's a jump discontinuity at x equals -1. Okay. All right. Over here, you remember this good old graph? Remember your old sine curve that comes through here? So if this is the opposite or the inverse of sine here, remember this is, or the reciprocal of sine, this is the cosecant graph. So this red graph is the cosecant graph. It has many discontinuities. All right, so it is discontinuous. And is infinite discontinuity because there are asymptotes on there, right? So infinite. And they happen at 0, pi, 2 pi, 3 pi, 4 pi, and so on. So they happen at every multiple of pi, where n is an integer. Okay, remember we wrote those things a little bit before. All right, so the next little bit is just a little bit of so you can see with your eyes that things are discontinuous, but this is the rule for a function to be considered continuous. All right, so for a function to be considered continuous at any point, there's 3 things that have to be true. All right, first of all, the function value at that point is defined. All right. So literally, like when I go on this graph here and I see x equals 1 is not defined, that breaks that rule. Over here, I see that at 3 it is defined. Now that's going to be bad for us, but look, it is defined at 3. The answer is 0. Okay, so that's what it means to be defined. Look back at your asymptote. At x equals 1, there's no answer here. This is an asymptote. So the graph stays away from it. It doesn't touch x equals 1. So that is not defined. All right. When I look here at x equals 3, there's the definition of it right there, -4. Okay. So the function has to exist there. It has to have an answer. All right. The limit of the function as you approach that number, the limit exists. So remember, limits don't exist if you approach different things. So like if you come from the right and the left and you have 2 different answers, that doesn't exist. If you go to infinity and negative infinity, it doesn't exist. All right. Now this limit exists. Look, so that limit exists, but the first rule was already, well, the third rule is going to be about to be broken. The limit and the value have to match up, so they basically have to be continuous. Okay. All right. So the last rule is that f of a has to equal the limit as x goes to a of f of x. So these 3 things make something continuous. And if you disprove any one of them, then you're like, okay, it's not continuous, it's discontinuous. And it has one of those types of discontinuities. All right, so let's look here. So this graph right here at x equals 2. So 2 is over here, so let's check it out. Is f of a defined? Yep, I see an answer right there. Step 1 done. The limit, does it exist? Yes, the limit looks like it's coming to like whatever 1.4, 1.6, something like that. And the limit and the function match each other. So it is continuous at x equals 2. All my 3 rules were met, and you have to just mentally think of those things. At -1, well, I mean, I'm sure you know this one, like it's when it's defined, so f of a is defined. The limit exists, it does not, because the right side and the left side disagree, so the limit does not exist. So no. Rule number 2 broken. And eventually rule number 3 is going to be broken also, because the function doesn't equal the limit from the other side. So anyway, but all right, so here, continuous at 0. So let's check at 0. There's a problem. it is at the function's value is -4. Does the limit exist? Yep. From the right side I approach -4, from the left side I approach -4. So it's defined, it exists, and they equal each other. So yes. And in fact, this is a nice polynomial, so it's continuous everywhere. Polynomials are all continuous everywhere. All right, over here, at x equals 1. So at x equals 1, let's check it out. I have a value for the function, so step 1, check. Step 2, the limit exists. So look, the limit comes to -1. The limit comes to -1 from the right. So step 2, check. But step 3, no good, or rule number 3. All right, the limit would come to -1, but the value of the function is way up here at 4. So step 3 is, or rule 3 is broken, so it's not continuous here. But at -2, everything seems to match up. The limit comes to -4, the value is -4, and they equal each other, so I would say yes to that. All right, so our last little stuff right here is just a little bit of like overall review in a way. So let's see. So I've labeled these with A's or G's, so meaning kind of like using algebra or like a graph. All right, so if I have a function, this is a nice polynomial, and I want to do a limit, just plug that right in. X to the third is 8, so I get 40. So 5 times 8 minus 6 times 2. So 40 minus, 12? So 28. Okay. Here, when I plug -3 in, I get 0 on top. 0 on top is perfectly fine. But when I plug -3 in here, I get 0 on bottom. 0 on bottom, bad. So I have to do one of two things. Or actually, I could look at a graph, all right, but I could also factor. And so when I factor this, the 3 comes out, I get x plus 3, and then on the bottom I have x plus 3 and x minus 3. So what cancels is these two. That was the part that was causing me to get 0 on top and 0 on bottom. So that was like the offending part. So I rewrite my limit. My function is now acting like this, 3 over x minus 3. So I can go ahead and plug that in. I'm going to get 3 on top because it's already there, and then -3 minus 3 is -6, so my answer would be -1/2. All right, so the next one. Okay, so let's think about this for a second. It says graph, so let's try that. X equals 4 is going to be an asymptote, so 1, 2, 3, 4. Now, the bottom is squared. So that means that all these answers are positive. Okay, and if you remember, 1 over x squared, if you graph it, looks like this. It comes across horizontal asymptote. My horizontal asymptote, 5 is on top, x squared is on the bottom, so I have a horizontal asymptote of 0. So it turns out this graph, you should kind of mentally be able to picture it. It kind of goes like this. All right, up, 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 up. So as I approach 4, both sides go to infinity. I mean, you can put it on your calculator, Desmos, but by now you should kind of get those things. All right, a log graph. So normally, a log looks like this, has an asymptote at x equals 0. This, however, has been moved to the left 2 spaces. So now that asymptote is at -2. And it's still kind of going along here. But somebody is asking me as I go to infinity. So as I go to infinity, it goes up, 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 up. And also you can imagine like the algebra. If you do logs of infinity plus 2, so if your numbers are getting bigger and bigger and bigger that you're doing the log of, your answers are getting bigger and bigger and bigger. I mean, pretty slowly, but they're getting larger. Okay. All right. Let's see, this guy. So a graph. So this is a exponential function. It's a growth. So let's look at a growth function. So we got growing. All right. And let's see. It has been moved up 4. And it's been flipped over. So that new graph would look like this. Flip over, so it looks like this, move up 4, so now it's kind of going like that. It might not be totally correct, but like we have the right idea. So this is 4. Okay, so what's the graph approach as we go to negative infinity? So anytime we have a horizontal asymptote, and we do, we have to watch out for that. If I had asked you to positive infinity, it would be going down. But negative infinity is going up towards 4, never really reaching it, but it's going towards 4. So that's our answer. Okay. Here we can use algebra or a graph. So I would like you to try on your homework to do it the algebra way just to practice it. But you can also, if you remember your asymptote rules, because this is asking for infinity, if you remember your asymptote rules, you can use your horizontal asymptote rules as well in the end. So look at these two pieces right here. So those two pieces right there, they match. So I would have my asymptote, my horizontal asymptote, is going to be 3/1. So this graph, whatever it does in the middle, it's going to approach and calm down to be 3 in the end. So that's going to be my limit as I go to infinity or negative infinity. Over here, same thing. Same idea. I can use my horizontal asymptote. As long as you're asking me to go to infinity, that's the end behavior of the graph. So this has a 4 and that has an x. So that means my horizontal asymptote is going to be y = 0. So this is going to be 0. But now let me show you the algebra way. The algebra way is this. You multiply the top and the bottom by 1 over the highest power in the denominator, so that'd be x squared. All right, so now we have our limit as x goes to negative infinity of this expression. 3x squared times 1 over x squared is 3. 1 times 1 over x squared is 1 over x squared. X squared times 1 over x squared is 1. This turns into 5 over x. And this turns into 2 over x squared. All right, so remember, anytime you have a constant number on top and the bottom has a power of x, that's just going to 0, kind of like this graph up here. Looks similar to that. So the bottom is increasing, to a super high or super low number, but 1 over a very large number is going to be 0. All right, and you're squaring it also, so that's even more positive. So like if you had $1 out of $1 million down here, you'd be like, oh, that's nothing to me. So these all go towards 0 when you do their limit, all 0. So what are you left with? 3/1. Over here, we're going to multiply the top by 1 over x and the bottom by 1 over x, because that's the largest power in the denominator. So I get my limit as x goes to infinity of 4 over x, and the bottom becomes 1, because this times that is 1. 5 times 1 over x is 5 over x. So just like before, this goes to 0, that goes to 0, so I get 0/1. Well, that's 0. So this is the proof down here, but like I said, that's where the horizontal asymptotes rules come from, but you can't know calculus before you do that, so that's why you just learn the rules that way. All right, that is it, and you have a worksheet for homework. I'll see you in class. Bye-bye.